Okay, it was throwout week this week around our area, and I managed to score myself 3 smart drive motors from the old Fisher and Paykel washing machines. We have 2 that are the same. These are the 60 series motors, and we call them that because they use the 0.6mm wire. These are a higher voltage motor than the earlier ones, and if you look carefully at the windings, they're not really neat. This one here is an older model. We call that an 80 series because it uses 0.8mm wire, and you can see that the wire is very neatly wrapped around each stator post. These ones here, the 80 and the 100 series, make the best generators for wind turbines and water turbines because they put out a lower voltage but a lot higher current. These ones here you can of course change by splitting each phase and then joining each split in parallel, so it'll halve the voltage but double the current output. But for this project it just so happens that this works out very well indeed, having 2 of the same and 1 a little different. So what I aim to do here is to have these 3 stacked one on top of the other, with one of these on the bottom and the other one on the top, and the one that carries the higher current, lower voltage, is going to be set in the middle. We're going to set this in a flyback charger type deal, and the bottom and the top one, if we're going to use magnetic polarities, will be firing a north pole. And I want to design it so when the coils are switched off and that magnetic field starts to collapse, the one in the center is going to fire up, and that will be the opposite pole being a south pole. And the idea is to see whether pulling the north pole down quickly with a south field results in a higher output on the flyback side to pulse charge our batteries. So top and bottom will be firing out north, and the center one will be firing south. So when these ones switch off, this one will be switching on, and this one will be separate, so we can switch that on, off, whatever we like, and we can then see if it makes a difference to the output on these 2. So the first thing on this project, because we want to stack these very neat and tidy and close together, we need to get rid of all these pins that are sticking up, which I've started to do on this one. So I'm going to go ahead and remove the rest of them and solder the wires in place like I have done with this yellow wire here, just so as they stack nice and neat. We won't have to worry about the center bit because that will actually sit inside the dish part here and not interfere with anything. So should be a fun project, and just a bit of research in the way that magnetic fields react with one another, and when whether or not there is an increase or decrease in output from these 2 when we pull the magnetic field down quickly with this one when it's in its flyback mode. So I'll go ahead, get rid of all this rubbish, put the wires on, and then we'll come back. I already have my studs cut, nuts and bolts ready to go to stack these, and that'll also give us some adjustment, and we can adjust the distance between each stator and see if that makes a difference throughout our testing as well. Back shortly. Alrighty, so we've got all our wires in place now. Also just grabbed the snips and cut the blocks off because they were standing up pretty high. All 3 phases are now in parallel, and we just have our 2 wires coming out of each unit. So these 2 here are identical, 7.7 ohms, 7.7 ohms. This one here is 4.3 ohms. so it's worked out quite fine. This one, of course, being the earlier model with a thicker wire, is going to be our centre coil. So what we've got to do now is these will just stack up like so. This one on top, and it'll end up looking something like that. Of course, we bolt the whole lot together with our studs and washers, which I've made a fair bit higher so as we can individually adjust the gap between each stator during our testing. So that's how it's going to end up. So this will be firing out a north field, this one will be firing out a south field, and this one will be firing a north field. So these two will fire at the same time, and as this side switches off and the field collapses, the centre one will fire up, which will be the opposite field. And what we're trying to achieve is to see if we get a stronger current from the flyback, or more power from the flyback, if we pull the north field down with the south field on this side. Of course it will be opposite on the other end. So if we're talking a magnetic flow, the two flows will be coming out and going in through the centre, out through the centre, and back out through the top and bottom. So it'll be like a double vortex, which we're going to call this the double vortex solid state generator. Nothing special about it. It's not going to be some free energy device or anything like that, although it may look impressive. It's really just 3 washing machine motor stators. The rotors, of course, we're not using because it's going to be solid state. So it's really just a test vehicle, you could call it, and who knows what we'll end up with. But so what I'm going to do now, I'm going to bolt it all together. And but just before I go and do that, I'm going to set one of the later model ones up just with a simple transistor and fire it from my signal generator, and just see what the magnetic field is like around the outside of it, using our little sniffer coil here with the LED on it. So we'll go and do that. I'll get it set up, we'll come back. Just going to do that as a bit of interest to see what kind of power we're going to be using to get some sort of field generated out here that's of reasonable strength. So I'll be back shortly. Okay, so we've just got a simple little transistor switch setup going on here that's being driven by my signal generator. We have 12 volts for our supply power, or voltage, and that's what's going to be going into our stator. The signal generator set at 4 volts peak to peak, but I have a 1.3 volt offset, so the transistor pulls off correctly. The frequency is 2 kilohertz, and our duty cycle is 30%. So that's the signal generator. That's what's switching the transistor on and off. 30% duty cycle. Our input voltage is 12 volts. Our current meter. I have a little sniffer coil here. I'm using a different one. I've put one with the steel core in there as it picks up the magnetic field a whole lot better than our air core coil. LED probes are polarity correct and have the LED coming on when this switches off, so it's actually feeding off the collapsing field is what's driving the LED. And you'll see for the other 60-70% of the time, the off cycle, that this coil will just ring a little bit. I found something interesting along the way, and to go into that a little bit, you'll see I have a bit sticking out that's just attached to one side of the coil, which is attached to the positive side of the LED. And I want you to watch what happens to the LED when we touch it to the steel core of our stator. Now, I have checked, rechecked and rechecked that the windings are not shorted onto the stator. They are totally isolated by these big plastic formers, which is all one piece, and there's absolutely no short from the core to the field windings. So we'll just fire up the signal generator. Our scope is hooked up. I have the blue channel across the collector emitter, which is why we have our 12-point-odd bolts there, and the yellow channel I've dropped down one division just to get it out of the way of the blue channel. The yellow channel is set at 5 volts per division, and our blue channel is set at 10 volts per division, and 10 times on the probe. So that's our scope setup, and of course the scope, as I mentioned, polarity correct across the coil, and DC coupling, of course. Invert is off on channel 1, DC coupling on channel 2, and invert is off on channel 2, and we just turn channel 2 completely off. So we'll fire it up. As you can see, I've got a fair bit of distance there. The LED is only just going, and it's not looking so good on the scope. Of course, our blue channel across the collector emitter, so you can see our 30% on time, and then it switches off and we get our flyback, and then the flyback drops down to an even voltage for quite some time, and we're at 5 volts but 10 times on the probe. So that's quite interesting. So we'll have 50 volts per division, so about 125 volts across those two neons for a fair period of time, as you can see. If I move the little sniffer coil close to, or near up to our stator, you can see the LED is now going quite nicely. And you can see the ringing in the coil when the LED is off is happening when the big stator is being fired up, and as soon as the stator switches off, you can see our LED on time. And we are drawing, it flicks between 75-76 milliamps at the moment. So a fairly decent flyback battery desulfator, if nothing else. I can of course increase the duty cycle and increase the output power. Last time I did that, I blew out the two neons and a transistor. So we'll leave it at the 30% duty cycle for this setup until such time as I get the rest of my transistors down, which should be here tomorrow or Friday hopefully, so we can build the whole setup. What I wanted to show you here was this little diggy that's sticking out, which is of course on the positive side. I'm going to touch that onto the core of the transformer, which is totally isolated from the windings. There is no short. I've checked it many times, and I just want to show you what happens both with our LED and the scope. So I'm going to touch that now, and you can see it gets much brighter. That is touching the positive side onto the steel of our stator. And our LED is now on for a 95% of the time at 3.8 volts, and that is why it's very bright. If I disconnect it, that is what is happening. So the positive of the LED is no longer touching the stator. That's what we have. I will now touch the stator with the positive side of the LED, or the core of the stator, and that is what happens. We do not draw any more power. Off, on, and our current does not move. That is off, that is on. Simply by touching the positive side onto the steel core of our stator, which once again is totally isolated from the windings. Absolutely no connection at all. On, off, and you can see the difference. So with it disconnected, it looks like that, and it's 2.6 volts max across the LED. And with it connected like that, the on time of the LED increases by the 30% off time, or on time of the coil or the stator, and the voltage across the LED is now 3.8 volts. And like I said, there is no change in current going into the device. I have tried putting the negative side onto the steel core and it does nothing as far as I can remember. Let's try it once again. I didn't actually turn the core around last time. I only placed a wire on the negative side. Okay, so that's touching it, and we are getting no difference at all. But if we touch the positive side onto the stator, we get a very large difference. So that's a little interesting. I've tried putting a voltmeter from here to the ground side, which of course is our emitter, and I get 0 volts. And I've also tried going from here, from the steel core to the positive side, and I get 0 volts, and yet when I touch the positive of the LED onto the steel core, well, you've seen the results. Anyway, so one interesting thing found already, and we haven't even finished constructing the device yet, which we're going to do next. We're going to get our studs, start bolting the three together, and we'll come back and have a look when the unit is assembled, ready for wiring all our different transistors up. The top and the bottom one are going to be fired with NPN transistors, and the middle one is going to be fired with a PNP transistor, and the reason for that is I can use my signal generator at a 50% offset to our square wave, so that ensures that one field will be firing up when the other two are collapsing. So I'll go ahead and put it back together, or assemble it as to how it's going to be, and we'll come back and have a look at the unit itself finished in the way of assembly, and we'll go from there. Alright, the whole unit's assembled. Looks quite impressive, doesn't it? But really it's just 3 stators bolted together, so although it looks impressive, it's nothing really fabulous. But anyway, this will be the end of this video. The next one, when the parts turn up, we'll make our drive circuits for our two sets of stators, of course, bottom one and the top one being one set and the centre one being the other, which will be firing in the opposite polarity. When these two switch off, that one will switch on, and vice versa. Trying to get some sort of AC magnetic rock going through the whole system. The reason I wanted to do this is I wanted to see that with the flyback systems, if we actually pull the magnetic field down using the opposite polarity, whether we get any more out of it or not. So things to come. One already interesting thing that I've found, as you would have seen, was simply touching the positive side of the LED to the core, which is totally insulated from the windings. If it wasn't, the scope and the power supply and the signal generator sharing a common ground, we would have sent 12 volts through the LED and blown it clean to hell. But I bet you think that's actually glowing, don't you? But it's not. It's a reflective light from the window. But yeah, that was quite interesting. Why did that get brighter? Simply by touching the steel core of our stator. Now the other interesting thing about that, after I was fooling around with it a little more, is it only does it between 1.8 kilohertz and 2.1 kilohertz. Anything above or below that, and that effect starts to fade off. So I don't really know what that was about. But anyway, that's it so far. I'll make up a base plate to bolt it all to. Put all these wires down through the bottom hole rather than out the top like they are. And once again make up our circuit to drive the whole system, and see where we end up. Thanks for watching, guys.